Hey guys, myself Tejas and I am studying in Sri Venkateswara College of Engineering. Today let's discuss about de Broglie's hypothesis, Heisenberg's uncertainty principle and wave function. Firstly, de Broglie's hypothesis. In the year 1924, French physicist Louis de Broglie extended wave-particle dualism through a hypothesis stating if radiant energy could behave like waves in some experiments and particles or photons in other, and since nature loves symmetry, then one can expect the particles like protons and electrons to exhibit wave nature under suitable circumstances. This is well known as de Broglie's hypothesis. Therefore, some sort of waves can be even associated with moving material particles called matter waves or de Broglie's waves, and the wavelength associated with matter waves is called de Broglie's wavelength. The wavelength of a photon in terms of its momentum is given by rho equal to lambda is equal to h by p. Hence, by analogy, the de Broglie's wavelength of matter waves is given by lambda is equal to h by p is equal to h by mv. Here m is the mass of moving particle and v is its velocity. For a particle charged or uncharged moving with kinetic energy E, the de Broglie's wavelength is given by lambda is equal to h by p, which is equal to h by square root of 2 me. For a charged particle accelerated with a potential v volt, the de Broglie's wavelength is given by lambda is equal to h by square root of 2 mqv. For an electron accelerated through a potential difference of v volt, the de Broglie's wavelength is given by lambda is equal to h by square root of 2 into mev. Further substituting the value of h, m and e, the de Broglie's wavelength is given by the expression lambda is equal to 12.27 divided by square root of v angstrom. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that it is impossible to simultaneously and precisely know both the position and momentum of particle. The more accurately you measure one of these properties, the less accurately you can know the other. The product of uncertainties is always greater than or equal to h divided by 4 pi. Mathematically, delta x into delta p is greater than or equal to h by 4 pi, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h is the reduced Planck constant. The principle challenges classical notations of determinism, emphasizing the probabilistic nature of particles at the quantum level. It underlines the profound impact of observation on quantum systems, as measurement inherently disturbs the state of a particle. Heisenberg's uncertainty principle fundamentally shapes our understanding of quantum mechanics, highlighting the elusive and probabilistic nature of particles, ch- challenging classical institutions about measurement, precision, and determinism. The principle highlights the inherent uncertainty in measuring these conjugate variables. The more accurately one property is determined, the less precisely the another can be known. Wave function. According to the de Broglie's hypothesis, the relation between momentum and wavelength is found to be experimentally valid for both photons and particles. The quanta of matter or radiation can be represented in agreement with uncertainty principle by wave packets. Thus, it suggests that concentrated bunches of waves must be used to describe localized particles and quanta of radiation, the variations of which make up the matter wave is called wave function. Properties of wave function. The wave function is subjected to the Heisenberg's uncertainty principle, which imposes limits on the precision with which certain pairs of observations like position and momentum can be simultaneously known. The wave function must be normalized, meaning that the integral of the squared magnitude of the wave function over all possible values of the variables is equal to 1. This ensures that the probability of finding the particle somewhere is 100%. In general, the wave function is a complex valued function. The complex nature allows for the representation of phase information, which is crucial in quantum interference phenomena. The absolute square of the wave function represents the probability density of finding a particle at a specific position. The probability of finding the particle within a certain region is given by the integral of sigma square over that region. Wave function can exist in superposition, meaning that a quantum system can exist in multiple states simultaneously. When a measurement is made, the system collapses into one of the possible states.